In the previous session, we have seen the basics of CMM, concept, the types of CMM, few applications of CMM and components. Now let us see the probes, the measurement process and few applications. There are two kinds of probes typically seen in CMM. One kind of probes are called as contact kind of probes. Another kind of probes are called as non-contact kind of probes. Contact type of probes means the probe comes in contact physically with the workpiece for measurement, as you see here. Whereas the non-contact probes, that will not come in physically contact with the workpiece to take the coordinate values. When in contact probes, when it touches in contact with the workpiece, it will take the coordinate of the center point at the moment of touching on the workpiece. Let us see one example, one kind of a contact type probe. These are typically called as touch trigger probe, or TTP in short. Touch trigger probe means, when the stylus comes in contact with the workpiece, during the hitting process, though it is a mild contact with the workpiece, there is that this stylus will be tilted. So when it is detached after measurement, when it is taken back, this stylus should go back to the position also. Touch trigger probe means the coordinate value at the moment of touching will be taken by the instrument, and that's why it is called as touch trigger. That means the measurement is triggered at the moment of touching. They use a particular kind of probe. The category of probes are called as a null probe. That means even if it is deflected during the measurement process, the probe will always be brought back to the center position. That is, the positional error is avoided, and this is done by checking by means of Wheatstone bridge arrangement. So the error because of residual stress or positioning will not be happening in the case of null probes. Let us see little more detail about touch trigger probe, its construction and its working. Touch trigger probes are electromechanical device that has ability to return the stylus ball to the same repeatable position followed after any deflection. This is a stylus that will come back to the original position, and that is called as null positioning. In touch trigger probes, there are certain elements called as pivotal plate here, that is spring loaded by an open coil spring here from the top, and the pivotal plates are supported on 3 location pivots, and where these are supported on ball points on bearings here. So what happens is, when the this stylus comes in contact with the workpiece, this will be tilted. While it is tilted, what happens is, one of the contacts of this bearing will be lost based on the direction of movement of the stylus. At that moment, the dimension of the three-dimensional space, or the coordinate of the three-dimensional space, is taken by the system, and that will be transferred to the controller for the computation. After this trigger event, the stylus ball will be removed from contact with the surface, and the arrangement is such that it will be brought back to the repeatable 0 position, so that the next triggering or the next contacting can be done. I have told you that the contact probes, where the workpiece is coming in contact, we have seen a touch trigger probe. There is one more example for contact kind of probe, that is continuous probe. In touch trigger probe, we can take points one by one. That is, if you hit on surface, it will take 1 point, it will hit on another point, it will take another point, whereas continuous probe will be taking continuous measurement when it is traced over the surface. So while touch trigger probes gather discrete points on surface, scanning systems, that is the continuous probes, acquire vast quantity of surface data, provides a clear picture of form and shape of the workpiece. Even a complex workpieces, the profile can be traced by a continuous probe. This images showing some physical appearance of different kind of stylus. These are the symbols, normal stylus, and stylus having a ball at the tip, right? This is a contact point, and there are star kind of probes also used. This is an indexable probe, that is, this probe can be tilted for measurement, and we can see the measurement positioning here from this. The typical contact probe material here, the red material that you see here, is a ruby. Ruby is typically used for many reasons. One is ruby is a gem material which is really hard, typically wear resistant, and dimension stability of the ruby for over a wide range of temperature is also very good, and these are the reasons why ruby is used. Let us see a few examples of non-contact type of probe where the probe do not comes in contact with workpiece, but it will take the measurement. How it is done, you see, instead of touching it, by using CCD camera, the image of the surface or the object to be measured can be grabbed to a screen. On the screen we can mark the dimensions or get the dimensions. This is another probe which is a laser probe. By means of laser, the distance is traced and the measurement is done with this arrangement. Now let us see how the measurement process is happening with CMM. We have to remember that all the CMMs are performing the measurements based on the sequence that we see here. The first measurement process that we have to do is the probe qualification. I have told you, probe qualification is the process of identifying the dimensions of the touch surface or sphere, contact sphere of a stylus. This is spherical in shape and it will have certain dimensions, and in order to know the dimensions of the stylus, what is done is the stylus will be brought to near to the qualifying sphere that is placed on the table, somewhere on the table on the CMM surface, and minimum 5 points are picked, like 1, 2, 3, 4 on the back side and on the top, so that the 5 coordinate points are taken by the system. You remember that when each point is touched, the center point of this sphere is taken by the system. So the system knows the information about the qualifying sphere, that is the dimensions, sphericity, error, etc. So once it is touched, getting this coordinate point, the system already know what is the dimension here. So this radius can be computed by the system. Similarly, this radius can be computed when the center point and the disk point on the sphere is known. Similarly, for all the touched points, the radial distance for this sphere, the contact sphere, will be taken by the system, and based on the computation and this data, the system will be arriving to the value of what is the radius of this sphere, that is stylus tip, and what is the sphericity error in this tip. That information is further used by the system for arriving at the dimension of workpieces further. So once probe qualification is the process of identifying the dimensions and form error of the probe that we are going to do the measurement. Second process is define the corresponding ideal form feature. That is, if you want to measure the radius of an object, we have to convey to the machine that we are going to measure the radius of curvature of a circle, so that when we touch many points on three-dimensional space, it will fit those points to a circular equation for the circle, and the circle will be fit, and based on the circle equation it will compute the values. Now the latest CMMs, these are very intelligent and these are using very intelligent software, such that you need not have to define what is the ideal form that is to be measured. By seeing the configuration of picking itself, the system will be arriving to what is a form feature that we are going to measure. So once we define the form feature, next point is pick point or coordinates on the object. Say if you want to check the measure the length of this cuboid piece, bring the stylus and touch the stylus on these minimum 3 points on this plane on the cube. Similarly, again define 3 points on this plane. Thus define this plane initially, then define this plane, save it in memory, and with this information if you ask for giving the length, it will compute the length between the surfaces. So I'll explain once again. If you know two points in three-dimensional space, say x1, y1, z1, and x2, y2, z2 in the three-dimensional space, and we have equation like this to compute what is the length between the points. Similar equations are used in CMM to compute distances, to compute radius, to compute any other parameter. So what happens is, when we pick the points, it will fit the points to ideal form, and it uses equations, and the computation is done based on the system software, and required values will be given. Even if you want the length, it will give the length. If you want to get the parallelism, squareness, anything, everything can be computed based on the equation given in the software. So the beauty is that both dimensional measurement as well as form measurement can be simultaneously obtained by just picking the points, coordinate points in three-dimensional space in CMM. I would like to tell you about another concept in CMM measurement that is called as compensated measurement and non-compensated measurement. See, I'll give you examples of compensated measurement. See, if we want to measure the length of this cuboid, I have told you that we have to define a plane like this by picking points here, and picking points here, we are defining the plane. Now we know that when the system touches on the surface, actually we want the distance between this surface and this surface, but what we get, this surface, okay, between this surface, but what we get is the center point. The system what takes is the center point of this point, center point of this, center point of this, and center point of this. So the distance that will be computed by the system will be originally like this distance. So to get the actual distance, what should be done is that after getting this length, this radius should be reduced from this side, radius should be reduced from this side. So we have to perform a compensation in this, that is, we have to perform a radius compensation in this, that is, the radius of the sphere on one side and the other side, that is, one diameter distance should be reduced from the actual computation, so that this required length will be obtained by the system. So this method used in the done in the CMM, where the dimension of the radius of the contact sphere is considered to get the actual dimension, is called as compensated measurement. This is another example for compensated measurement. Suppose if you want to measure the diameter of this or radius of curvature of this, what actually we get by picking the point on the circumference of circle is the radius of this circle that you see in the dotted line. To get the diameter of the actual circle, the radius should be reduced from this. So here also you are reducing the diameter of the spherical surface so that the actual radius is obtained. Okay. Here also the compensation done in two different directions. That's very interesting. You see here, that is, if you say this is a tube having in inner side it's vacuum, it's no material, there is this vacuum here. So if the diameter of this cylinder and this cylinder are to be taken, what should be done is, conventionally as we perform the measurement, pick many points on the circumference of the cylinder so that this radius can be obtained by reducing the radius of the circle fit by the system. But here the radius should be reduced, whereas in this case, if you want to check get the diameter of the inner circle, what you have to do is, you have to you are picking the point, that is this center point, this center point, so this center point, these three center points are taken minimum, and a circle is fit like this through this, but the radius, this is a circle that is fit, but in order to get the actual circle, this circle, what should be done is, with this circle the radius should be added. That means compensation should be done in the positive direction. Here the compensation is done in the negative direction. So depending on the direction of measurement, compensation should also be done. And in all the cases, compensation need not be done. That's if compensation need not be done to get a required measurement, is called as non-compensated measurement. An example is here. See, if you have a workpiece like this and if you are interested to get the angle between the surfaces, you can define this plane, you can define this plane, and angle between the plane, this angle is same as that of the actual angle. In this case, you don't have to worry about the compensation should be done in this direction. Similarly, if you want to measure the distance between the centers, here there is one center here, there is another center here. So for that you have to define this circle initially and define this circle initially, and when we get the distance between the circle, even if the circle is bigger or smaller, if you are, even if you are picking at the inner side, the center of the inner circle and the actual circle are same. So do not have to worry about this. That is, for center measurement, compensation need not be done. So compensated measurement means actual measurement is obtained by considering the dimension of the probe, and the dimension of probe is compensated to get the actual measurement. Whereas non-compensated measurements, where we need not have to consider the dimension of the probe, so probe compensation need not be done. Some features of non-contact CMM. In non-contact CMM, the image taken by the CCD will be displayed on a computer screen where you can place the cursors, and by suitable image processing you can get the dimension. Here the problems are, when we perform the measurement, the lighting should be good such that the shadow should be eliminated. Shadow should not happen in the image. If there is shadow in the image, that can lead to further wrong measurement. Focusing on inclined surface or workpiece for the measurement is also a problem. We know that if surface is inclined, focusing can be different on different surfaces, on different heights, depending on the distance between the lens and the surface. So in such cases, the measurement with non-contact CMM is difficult rather than difficult, that there can be error in the measurement. And most of the time this measurement will be done manually by seeing the image on this, so that can lead to manual error also. So with this previous discussion of this session, let us again need to have a review. Let us see few questions. Try if you can give answer for these questions. You know what is meant by touch trigger probe? Can you provide few examples of non-contact kind of probes? What is meant by null probe? What is meant by probe qualification? What are the steps involved in measurement with CMM? Okay. If you are able to answer these questions, well, we can go ahead. Otherwise, please go back and verify and learn it and come back. Let us proceed after that. Now another topic that is beyond the syllabus as per the university curriculum, that is errors in CMM. Just for your information, we say that CMM is a very accurate instrument, having least count of even 0.1 micron. So is there any error in measurement? Obviously yes, any instrument will have error. So what are the kinds of error that can happen in CMM? There are two kinds of errors when we categorize it. One is spatial errors, errors in the measured position, or there can be computational errors also. Spatial errors are due to the error in guideways, in the scale, in the probe system, error in the qualification sphere, etc., etc. Error can happen because of the environment, magnitude and direction of the probing force. Sometimes we may hit the workpiece surface of the probe with uncontrolled force. It should have a controlled force, but sometimes it can slip. So that can also lead to error. Then if you do not choose a stylus appropriately for depending on the requirement of the workpiece and the measurement, there can be error in the measurement process. So it needs expertise to choose the right stylus. There can be computational errors also, software error in the estimating geometry of workpiece. There can be error with the number and relative position of probed points, etc., etc. There are certain geometric errors also with CMM. It is identified that there are 21 sources of errors in CMM, kinematic errors. 21 sources of error means for one axis itself, there can be one positional deviation in the direction of motion. There can be two linear deviation, that is perpendicular to the direction of motion, straightness errors. There can be three angular deviation for the same axis, like a roll, pitch, and yaw kind of error. That means 1 plus 1 error here, 2 here, 1 plus 2, 3, 3 plus 3, 6 errors in one axis itself, like that for three axes. Sorry, here it's okay, 3, okay, 6 errors in one axis itself. 6 into 3, 18 errors happening uh, in 3 axes. Apart from that, there are 3 other errors also, 3 squareness errors between the pair of axes. So there will be 21 errors. Let us see a few examples of measurements that are done commonly with CMM. This is a cantilever CMM that is used for checking the measurement of a cylinder. Okay, you can see that there is a robotic arm kind of CMM that is used for measurement of this object. Okay, continuous probing is done to check the circularity of this thing. Now gantry type CMM here, see a gantry type, it is measuring some features of an assembled bike. A column type CMM is now used in this diagram to check the dimensions of an assembled cabin of some automobile vehicle. There is a twin column CMM, automated CMM, that is checking whether the dimensions of an assembled car before delivery. Non-contact probes shown here that verifies the profile of a door of a car. Okay, continuous probing is done. Continuous profile is done here. Few examples of companies which are making CM: Tessa, ME312, Helmel, International Metrology Company, Faro, Leitz, etc. Few of the companies that makes CMM worldwide. Now, based on the discussion, students will have to go to the learning material that is provided. Students can post their questions in our academic management system for further discussion.